Okay, so in this video, I'm going to look at determinants. Just a little historical note. Matrices arose as an attempt to solve systems of equations. There was no sort of forethought to it. It was just discovered through one method or another that this was a good way to do things. And determinants have been studied as a property which arose from matrices. And I have one of these books. It's pretty funny. Interesting. It's interesting. This is published originally in 1882, and this is sort of a reprint. So you can just pick sections of text from old. I love old math textbooks. I'm nerding out right now. Here we have it. If a particular form of algebraic expression be lengthy and of frequent occurrence, it becomes desirable to introduce a suggestive name and symbol for it. And if the form be one of a family, it is also desirable that the names and symbols of all of them should indicate this relationship. Such a nomenclature and notation are advantageous not merely from the convenience thereby afforded in speaking and writing, but as helps to the actual discovery of the properties of the forms in question. Anyway, then it goes on and on. But I don't know. I'm nerding out. I love old textbooks. That one's a combination of math textbook and Old Testament. So cool. Anyway, on to the actual problem. So just a little bit about determinants in general. In general, a determinant can be found, well, let's start with a 2 by 2. So we've got some elements here, A, B, C, D. Maybe you've seen this before. So let's say A is this matrix here. Determinant of A. Sometimes, I think is it square? No, I think it's sometimes just those. But anyway, it is, there's a closed formula for it. It's AD minus BC. There we have it. But another way we can look at it is take this bit here and apply sort of a mask of plus minus plus minus, then take a row or a column and expand along it. So this should be plus minus, shouldn't it? Okay. So the first thing I see is A. So I strike out the row and column of A, and that gives me D. So I have positive A times D, and then I take the next element in the row, which is B, but there's a negative in that position on the mask. So we apply that, negative B, strike out the row and column, we're left with C. And that's how it works. Now let's have a look at a 3 by 3, A, B, C. Okay. So we have a similar mask of factors. Plus, minus, plus is just alternating. Just like that. And it really actually doesn't matter so much what the other elements are because I typically always pick the first row. So we go across this first row. I have A that has a position of positive. So I take positive 1 times A, strike out the row and column, and what's left is this little 2 by 2. And we actually take the determinant of that 2 by 2. Then I have B, but B has a corresponding negative sign, so minus B, strike out the row and column, and insert the elements which are remaining, plus C, strike out the row and column. There we have it. Okay, so let's go through some examples. Remember I said that we can sort of use a determinant to check whether a system is solvable. So we'll go back to our first matrix. Okay. To get the determinant, again, we'll expand across the first row. So we have 1 times this bit here, 1, -3, -7, 1. Okay, then we have -2. Apply the mask of -1, so that becomes +2. Plus, then +1 times 1, 2, 1, 4, -7. Okay, now I'm not going to go through the expansion for these because we simply have a closed formula. It's the diagonal minus the off-diagonal elements. So again, we have 1 times 1 minus 21 plus 2 times 2 plus 12, that's minus negative. Biggest mistake I see people making is messing up the signs here, so just be mindful of that. And we have -14 minus 4. Okay, so we have -20 plus 28 plus -18, which comes out to -10. And that's it. That's the determinant of a 3 by 3. Let's do some more examples. Okay, so this matrix corresponded to a system which was not solvable. Let's see if we can compare and contrast to the previous one. Okay, so we'll go ahead and expand these 2 by 2 determinants. And as you can see, like clockwork, everything comes out to 0. It's interesting. Okay, let's have a look at the next example. These coefficients will all be 1, so actually I'm just going to ignore them. Okay, and similarly, this one comes out to 0 as well. And this was a matrix for a system which had an infinite number of solutions and no inverse. So it turns out that if a determinant is 0, the matrix has no inverse. If the determinant is anything other than 0, the matrix has an inverse. And there's sort of an analogy here. Now, if we take a shape and we hit that shape with a transformation, let's call that t. So each of the points on this shape undergo a transformation by the matrix T. Could do all sorts of weird things to the points. We have an original area, an old area, and a new area of the shape. And it turns out that the factor, so if we go area new over area old, that shrinking or scaling factor is equal to the determinant of the matrix T. So the inverse would correspond to sort of blowing it back up. Now, if that shrinking factor is anything other than 0, then you can, take the reciprocal of it, and that will take you back to the same original area. If the determinant is 0, then that corresponds to sort of taking this and transforming it to some sort of shape which has 0 area. So that could be a point, or it could be a line or something, but somehow we've lost some information. We can't take this line and blow it back up to have an area. We can't take this point and blow it back up to have an area. Simply not possible. So hopefully that helps you to sort of get your head around it. And yeah, so that's it. So In this video, we had a look at determinants and the importance of determinants, and it's actually going to come back later on when we look at calculating the cross product, but I'm going to leave that for now. So hopefully you found this useful and maybe not entertaining, at least educational, and I'll see you again soon. Bye.